Everything we know, every planet, star, and galaxy, is thought to have originated from a single moment, the Big Bang. In that instant, the universe seemingly burst into existence from nothing and rapidly expanded into the vast cosmos we inhabit today. But a natural question is, how could something arise from nothing? What triggered this event? And if there truly was nothing before the Big Bang, what does nothing even mean? Was there an empty void quietly waiting for the universe to appear? Or is that state of nothingness so bizarre that our current physics cannot even describe it? Some theories even suggest that the Big Bang was not the absolute beginning, but just one phase in a larger picture. Perhaps something existed before it. From quantum fluctuations and extra dimensions to bouncing multiverse models and periodically expanding universes, various scenarios attempt to answer what ignited all of existence. Tonight, we will explore the major theories of cosmic origins, from the cyclic universe to quantum tunneling, and analyze the scientific challenge of what lit the Big Bang. It's a vast story, but before we dive in, please don't forget to like and share. Traditional cosmology has long treated the Big Bang as the absolute starting point of the universe. In this approach, time, space, matter, and energy all originated at a single, extremely hot, and dense beginning. However, with the development of modern physics, serious consideration is now being given to the possibility of a cosmic landscape that predated the Big Bang. The challenge is that we have no direct observational evidence from before the Big Bang. Light, radiation, and matter information can only be traced back to the universe's earliest moments, and anything before that lies beyond the reach of our telescopes and detectors. Nevertheless, theoretical models allow us to extrapolate backward mathematically, painting possible scenarios and imagining what the universe might have looked like before it exploded. One hypothesis suggests that the universe existed in a timeless quantum embryo before the Big Bang. In other words, there was no ticking clock in the sense we are familiar with, and no clear before and after. Instead, there was a holistic state dominated by quantum uncertainty. Rather than a hot, dense point-like beginning, it was more like a quantum fluctuation existing within a larger energy field. According to quantum mechanics, even what we perceive as empty space is never truly empty. Quantum fields continuously experience fleeting fluctuations, like small ripples periodically rising on a water surface. If one of these quantum fluctuations reaches a certain critical threshold, it could trigger an event massive enough to cause space and time itself to emerge from this pre-existing quantum background, thus giving birth to our universe. Other theories propose that our universe is just a sub-world within a higher dimensional structure. Under the framework of string theory, the universe may contain more than the familiar three spatial dimensions plus one time dimension, potentially including several hidden extra spatial dimensions. In some models, what we perceive as the Big Bang could be the result of a collision between high-dimensional membranes, or brins. These brins are thought of as gigantic sheets or films floating in a higher dimensional bulk space. When two brins approach each other and collide, they release immense energy, creating a new universe with its own space, time, and physical laws in the collision region. If this approach is correct, our universe is merely a bubble in a higher dimensional world, and the Big Bang was a local event in this greater structure. The theory of cosmic inflation posits that the universe underwent a period of extremely rapid expansion. Its volume ballooned exponentially, in a tiny fraction of a second immediately after the Big Bang, before settling into its slower expansion phase. However, some inflation models go further, suggesting that inflation itself may predate the Big Bang, existing in a timeless quantum state where random quantum fluctuations determine when and where a new universe bubble is generated. If this is the case, then what we typically call the Big Bang is not a unique singularity but just one ordinary ignition event among many inflating regions. The process of inflation could be continuous in different parts of the cosmos, perpetually generating new baby universes. Taking this one step further leads to the idea of the multiverse. Our universe is merely one member of a vast collection, where different universes may not be directly connected and could possess different physical constants, numbers of dimensions, or even entirely different fundamental interactions. Some universes might quickly collapse, others might expand forever, some might not allow for the formation of atoms and galaxies, and others might be more conducive to life than our own. In these more daring hypotheses, before the Big Bang, there may not have even been space, time, or matter, but only some more fundamental information structure or unknown set of mathematical physical rules. Our familiar universe would then be a manifestation or projection of these deeper rules. If so, understanding what happened before the Big Bang requires not just new telescopes or particle colliders, but a complete overhaul of how we think about existence itself. Of all the ideas that have shaped our conception of the universe, one of the most counterintuitive is that empty space is not empty at all. For most of human history, a vacuum was considered true blankness, no matter, no energy, no structure. Ancient Greek philosophers debated whether a vacuum could exist, and early scientists imagined the vacuum as an entirely static background stage upon which objects moved, but which was itself devoid of content. Up until the 19th and 20th centuries, it was still widely assumed that cosmic space was a silent, empty vacuum, where nothing happened, and bodies merely traversed it in solitude. However, the rise of quantum physics in the 20th century revealed a profound truth: what we call empty space is far from empty. The so-called vacuum is actually a restless, fluctuating ocean of quantum energy, filled with unseen energy and fluctuations. This is true even in regions completely free of matter and radiation. Even in the coldest, most isolated corners of the universe, space itself remains active, subtly trembling in the dark. The void we once assumed to be nothing conceals an incredibly rich structure. The core of this realization is the concept of quantum fluctuations. In classical physics, a vacuum is imagined as absolutely static, a state of zero energy. However, quantum mechanics tells us that at the most minute scales, uncertainty prevails. The famous Heisenberg uncertainty principle states that we cannot simultaneously know the energy and the duration of a system with perfect precision. This implies that the energy value in the vacuum can never be exactly zero. The result is that the space constantly experiences brief bursts of energy, suddenly popping into existence and disappearing back into the quantum vacuum in an extremely short time. Even though these fluctuations are not visible to the naked eye or detectable as concrete particles, the energy ripples are continuous. These fluctuations can spontaneously give rise to a special kind of existence: virtual particles. Unlike the atoms, electrons, or quarks that make up everyday matter, virtual particles only flash into existence for the briefest moment before rapidly submerging back into the quantum vacuum, too fleeting to be directly observed. But the fascinating thing is that while we cannot see them, their effects can be measured and align perfectly with theoretical calculations, proving they are indeed at work behind the scenes. One of the most famous examples is the Casimir effect. In this experiment, scientists place two uncharged, parallel metal plates very close together in a vacuum. According to classical physics, if no external forces are present, they should remain stationary. However, experiments show that the two plates are gently pushed toward each other by an invisible force. Why? Because the pattern of quantum fluctuations is different between the plates compared to the external space. Fewer modes of virtual particles are allowed to exist between the plates, resulting in a slightly greater quantum vacuum pressure on the outside, which gently pushes the two plates together. This force from nothingness is direct evidence of quantum vacuum fluctuations. Another phenomenon closely related to the quantum vacuum is vacuum polarization. Even in a vacuum, virtual particles are continuously created and annihilated, and they can influence the behavior of real particles. For example, when an electron moves through space, it doesn't travel alone but is surrounded by a cloud of virtual particles. These virtual particles subtly modify the electron's charge and mass. High-energy physics experiments have observed these effects, confirming once again that the vacuum is not nothing, but a dynamic, complex quantum environment. Some scientists believe the vacuum itself might hold the key to explaining dark energy. Observations show that the distances between distant galaxies are stretching at an ever-increasing rate. The universe's expansion is accelerating. This contradicts traditional models relying only on gravity. One possible explanation is that the vacuum is filled with some form of energy that exerts a repulsive force, pushing the universe to accelerate its expansion. This energy, sometimes called vacuum energy or the cosmological constant $lambda$, is likely one of the sources of dark energy. However, the energy density of the vacuum predicted by quantum theory is many orders of magnitude larger than what is observed astronomically. This vast mismatch, sometimes called the vacuum catastrophe, is considered one of the biggest problems in modern physics. If the vacuum truly contains such astounding energy, why does its overall effect on the universe's evolution seem so mild? If its true value is small, what mechanism tuned it to that value? The deeper we study the quantum vacuum, the more we realize that what we once thought was empty is actually a rich quantum sea, where energy and fluctuations are quietly shaping the fate of the entire universe. Even in the coldest, most isolated regions of the cosmos, where there seems to be nothing, space is never truly quiet. Quantum theory tells us that any quantum system has a lowest possible energy state, known as the zero-point energy. Even in this lowest gear, quantum fluctuations do not completely vanish, the vacuum still subtly trembles. One important idea associated with zero-point energy is spontaneous symmetry breaking (SSB). In physics, symmetry means that a system's properties remain unchanged under a certain transformation. For instance, a perfect circle looks the same from any angle, giving it rotational symmetry. But in some cases, a system that is initially highly symmetrical will select a specific state due to minute internal disturbances, thereby breaking the symmetry and giving rise to new structures or properties. Imagine a perfectly symmetrical hill with a ball resting quietly at its apex. Theoretically, the ball is perfectly balanced, and the situation is symmetric in all directions. If undisturbed, it could remain there indefinitely. But in reality, even the slightest breeze or vibration will push the ball to one side, causing it to roll down the slope. The rules of the hill itself haven't changed, the symmetry still exists, but the system's actual state has broken that symmetry, as the ball chose one direction to roll. In the universe, a similar process may occur on an unimaginably grand scale, triggered by tiny quantum fluctuations and zero-point energy. In the immediate aftermath of the Big Bang, the universe was extremely hot, high in energy, and full of quantum fluctuations. As expansion and cooling occurred, these fluctuations began to drive phase transitions in certain fields, much like water freezing into ice. At the initial extreme temperatures, it is hypothesized that all fundamental interactions, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, may have been unified into a single, superforce. But as the universe's temperature dropped, a series of spontaneous symmetry breakings occurred. First, gravity separated from the whole, then the strong interaction separated from the electroweak interaction, and later, the weak nuclear force and electromagnetism went their separate ways. It is these symmetry-breaking events that led to the familiar configuration of the four fundamental forces we have today. The most famous example among these is the Higgs mechanism. According to this theory, at the high temperatures of the early universe, all particles were initially massless and moving freely, a highly symmetric state. But as the universe cooled, a quantum field that permeates all of space, the Higgs field, underwent a spontaneous symmetry breaking. At this point, the Higgs field was no longer the same in all directions. Some particles interacted strongly with it, slowing their movement, which manifests as their gaining mass. This process was also accompanied by the appearance of a new particle, the Higgs boson. Without this symmetry breaking, particles would have no mass, atoms could not form, and stars and galaxies would be impossible. The universe would likely be a structureless soup of radiation. During the period of cosmic inflation, the universe expanded at a rate far exceeding today's speed. Some theories suggest that a sudden change in the state of the quantum vacuum triggered this inflation. The energy density in the vacuum, existing in a false vacuum, or quasi-zero-point energy state, was abruptly released, causing space to stretch violently like a balloon. If so, zero-point energy and vacuum fluctuations played a central role in the formation of the universe's large-scale structure, determining which regions would be slightly denser and which slightly sparser, eventually evolving into galaxy clusters and cosmic voids. However, the nature of zero-point energy is still far from fully understood. What is the relationship between vacuum fluctuations, cosmic inflation, and the Big Bang? Is the dark energy we measure today closely related to this vacuum energy? These questions remain at the forefront of research. If the vacuum is not a cold, passive background but an active participant in cosmic structure, then to understand the Big Bang itself, we must regard the quantum vacuum as one of the main characters in the story. In the classical physics approach, space is often viewed as an empty stage, and time is a straight line flowing uniformly from the past to the future. Objects and events perform on this stage, but the stage itself is not part of the drama. However, quantum physics suggests that at the smallest scales, space and time may not be inherently fundamental entities, but rather the result of deeper quantum processes emerging into existence. One key idea is that spacetime may originate from quantum entanglement. Quantum entanglement is one of the most mysterious phenomena in quantum mechanics. When two particles become entangled, any change to one is instantly reflected in the other, regardless of the distance separating them. Numerous experiments have confirmed the reality of entanglement, making it a fundamental feature of the quantum world. Some physicists propose that if enough quantum systems are entangled with each other, the network of their relationships could weave the structure of space that we perceive. In this view, space is no longer a passive container but is made up of the entanglement relationships between countless quantum systems, a vast quantum network that, on the macroscopic scale, appears as continuous, smooth three-dimensional space and one-dimensional time. On large scales, this network looks like the continuous spacetime we are familiar with, where distances can be measured with a ruler and time with a clock. But at extremely small scales, space may be grainy or discrete, similar to the pixels on a digital screen, where further division loses meaning. Another line of thought is that spacetime, particularly time, may emerge from quantum uncertainty itself. At the smallest scales, nothing is truly still. Particles and energy are constantly appearing, disappearing, and fluctuating. If there was no fixed coordinate grid or time scale to begin with, only a quantum background filled with fluctuations, then in the universe's earliest phase, concepts like distance, direction, before, and after, may have been meaningless. This state is sometimes referred to as pre-spacetime or the pre-geometric phase. It can be likened to water being a fluid, amorphous liquid before it freezes. When the temperature drops below the critical point, water molecules arrange into an orderly lattice, and the macroscopic structure of ice emerges. Similarly, the universe may have undergone a phase transition at some point, solidifying the ordered structure of spacetime from a chaotic fog of quantum fluctuations. In theoretical frameworks like loop quantum gravity, space is further hypothesized to be composed of incredibly tiny loops or quantum volume units. Image illustrating the structure of spacetime in loop quantum gravity is a network of loops. It is no longer a continuum that can be infinitely subdivided but resembles a network woven from discrete line segments and nodes. Each loop represents the smallest unit of space, and together they form the macroscopic structure that appears continuous. Time itself may also not be an absolute, unified external clock, but is intimately related to the changes and evolution within the system. In the macroscopic world, we are accustomed to thinking that time always flows one way, the past is irreversible, and the future is yet to come. But at the quantum level, the order of events sometimes becomes fuzzy, and the evolution of some systems is difficult to describe with a strict sequence. There is a view that the arrow of time is closely linked to the increase of entropy. The universe moves from a more ordered state to a more disordered state, and this overall trend gives time its direction. In the very early universe, when the cosmos was in a highly ordered, almost simple state, time may not have been as stable and defined as it is now. Only as the universe gradually expanded and structure became complex did the forward progression of time become a stable macroscopic phenomenon. The questions become even more intriguing when we connect these hypotheses to black holes. Classical general relativity describes a black hole as a region where the geometry of spacetime is so extremely stretched and warped that even light cannot escape. However, if space itself is composed of quantum connections, the interior of a black hole may not be a simple void or singularity, but potentially a knot of an extremely dense, intricately complex quantum entanglement network, perhaps even connected to other regions of the universe. If, at some stage, both space and time had not yet formed, then the Big Bang might not be viewed as a point explosion, but rather as a quantum embryo gradually unfolding into structured spacetime. Ideas similar to the holographic principle even propose that the three dimensions of space and time we perceive might be the projection of some higher dimensional, more fundamental layer. At that deeper level, spacetime is not the most fundamental concept. Currently, physicists are searching for potential traces left by these hypotheses through methods like gravitational wave observations and high-energy particle collision experiments. If we truly find evidence that spacetime is not fundamental, it would mean that our understanding of existence needs to be fundamentally rewritten. For over a century, physicists have struggled to understand and unify the two pillars of theoretical physics. 1. Quantum mechanics (QM), the theory that describes the strange behavior of particles in the microscopic world. 2. General relativity (GR), the geometric theory that explains gravity and the structure of the universe on large scales. Quantum mechanics reigns over the extremely small scale. Electrons can be in multiple places at once, a particle's state is in a superposition until measured, and reality is probabilistic rather than deterministic. General relativity, meanwhile, governs the macroscopic world. Planets orbit stars, galaxies cluster together, and spacetime is curved by mass and energy. Gravity is no longer a traditional force but the curvature of spacetime geometry. In GR, spacetime is viewed as a smooth, continuous fabric. Massive objects cause this fabric to sag or curve, and nearby objects follow the curved path of spacetime. This is the force we perceive as gravity. This description has been confirmed by numerous observations, such as the bending of starlight near the Sun and the gravitational waves produced by the merger of binary black holes. However, quantum mechanics tells us that at the smallest scales, the world is violently fluctuating and full of uncertainty. Particles have no definite trajectory, only probability distributions, and physical quantities like energy, position, and momentum are subject to an irreducible uncertainty. Spacetime in this context cannot be absolutely smooth. The trouble arises when we attempt to consider quantum effects and gravity simultaneously. The mathematical structures of the two theories clash severely. If we try to treat gravity as a quantum field, similar to how we treat the electromagnetic force, calculations often yield results that are infinitely large, divergent, which cannot be tamed by conventional renormalization methods. This indicates that we are missing something more fundamental. In most scenarios, GR and QM work perfectly well on their own. Use general relativity for everyday and astronomical scales, and quantum theory for atomic and subatomic scales. But when entering extreme situations, such as near the center of a black hole or the ultra-high energy density state at the beginning of the Big Bang, both theories must apply simultaneously, yet they contradict each other. This has prompted physicists to search for a unified framework, known as a theory of quantum gravity. One candidate is the previously mentioned string theory. In string theory, the fundamental entities are no longer point particles but extremely tiny one-dimensional strings. Different modes of vibration manifest as different particles. One mode might look like an electron, another might be a photon, and yet another might correspond to the vibration of the hypothetical graviton. In this way, gravity and other interactions are all viewed as different manifestations of the same underlying structure. Image illustrating a fundamental particle as a vibrating string. String theory requires extra spatial dimensions to be mathematically consistent, usually totaling 9 spatial dimensions plus 1 time dimension. These extra dimensions are thought to be curled up extremely small, so we don't perceive them in daily life. Their shape and size influence the vibration frequencies of the strings, thus determining particle properties like mass and charge. However, string theory currently lacks direct experimental verification. We have yet to observe extra dimensions or find direct evidence of the strings themselves. Another path is loop quantum gravity (LQG), which starts from general relativity and attempts to quantize spacetime itself, viewing space as a network of discrete loops. This approach mathematically avoids certain infinite divergences, such as those at black hole singularities. However, LQG also lacks direct experimental support and is still under development. Some researchers place their hope on black holes and the early universe. General relativity predicts a singularity at the center of a black hole, a point of infinite density where the theory breaks down. Quantum mechanics suggests that infinity often means a model is incomplete and that new physics should intervene. In the 1970s, Stephen Hawking combined quantum theory with general relativity and found that black holes are not absolutely black. Quantum fluctuations near the event horizon cause black holes to slowly radiate energy. This is the famous Hawking radiation. This raised a startling problem. If a black hole eventually evaporates and disappears, what happens to the information that fell into it? Quantum mechanics insists that information cannot be utterly destroyed, while the classical approach of general relativity seems to imply that information is swallowed and never escapes. This is the black hole information paradox. To resolve it, some propose that a black hole might act like a holographic screen, encoding all of its internal information on the surface of the event horizon. Similarly, the entire universe might be a form of holographic projection. Deep quantum information is encoded on some boundary, and the three-dimensional world we see is merely its unfolding. Furthermore, since the first detection of gravitational waves in 2015, these observations have been used to test the correctness of general relativity under extreme strong field limits. If future gravitational wave signals reveal subtle deviations from the existing theory, it could provide crucial clues for a quantum gravity theory. In summary, to truly understand the physics before the Big Bang, inside black holes, and in the universe's most extreme states, we must find a way to unify quantum mechanics and general relativity, allowing spacetime and quantum mechanics to appear in the same script. In the standard Big Bang model, the universe is thought to have been born about 13.8 billion years ago from an extremely hot, dense state, where the coordinate of time was set to 0. But when we push the equations of general relativity backward to their limit, we encounter a singularity where physical laws break down. This suggests that the approach of viewing the universe as being created at a single moment might be incomplete. To address this problem, physicists James Hartle and Stephen Hawking proposed a bold hypothesis in the 1980s, the no-boundary proposal. Image illustrating the no-boundary proposal with a smooth, closed shape instead of a sharp starting point. Instead of treating time as starting from an absolute beginning, they proposed that in the very early universe, the nature of time changed, merging with space, thereby avoiding a starting point. In this model, the universe did not have a hard boundary beginning, much like the North Pole on Earth's surface. If you walk north along the Earth's surface, you eventually reach the North Pole, but going further north is meaningless because the North Pole is the terminus of all northern directions. Similarly, in the no-boundary proposal, as we extend the time coordinate all the way back into the past, we eventually reach a state where time no longer flows as we are accustomed to, but gradually becomes like an extra spatial dimension. In other words, rather than asking what happened before the Big Bang, one could say that before that, the concept of time was no longer applicable. The universe was not started from a sharp zero point but smoothly transitioned from an early, smooth, finite, but unbounded quantum state into the expanding universe we see today. Mathematically, the no-boundary proposal introduces the concept of imaginary time, $tau. We usually view time as a real number line, the second hand moving from past to future. But under extreme conditions, such as the very early universe, time can be treated as part of the complex numbers, having an imaginary component. This allows us to treat the time dimension mathematically in a form similar to a spatial dimension, making the overall geometry of the universe a smooth shape without an edge or a classical singularity, like a sphere or a closed curved surface. The philosophical implication of this hypothesis is profound. If the universe is a self-contained whole with no explicit starting point, it does not require an external prime mover. The universe exists because quantum mechanics and general relativity permit such a solution to exist, not because of some external event that ignited it at a certain moment. Of course, this proposal also raises many questions. If time was like space in the very early universe, how did it transition into the unidirectional flow of time we experience today? And what laws determine the shape of that early quantum state? It is currently difficult to directly observe the universe at such an early stage, but clues may be hidden in the cosmic microwave background (CMB) radiation. This is the afterglow left over shortly after the Big Bang, and the tiny temperature fluctuations within it record details of the early universe. By precisely measuring these fluctuations, scientists hope to determine if the universe's initial geometry aligns with the predictions of the no-boundary proposal. If the Hartle-Hawking proposal is correct, the universe did not suddenly pop out of nothingness but naturally blossomed from a smooth quantum state into the magnificent cosmos we observe. In this way, traditional questions about who created the universe or what came before it may become inapplicable. The more appropriate question would be, what quantum laws make such a universe geometry possible and stable? The standard Big Bang model describes a dramatic event that ignited the universe, after which the cosmos expanded, cooled, and gradually formed structure. Eternal inflation theory further proposes that the inflation that occurred in the early universe may have never truly ended on the whole. In the inflation approach, space is filled with a field similar to vacuum energy, which causes space to expand at an extremely high rate. The observable universe we inhabit may be just a small region where inflation has stopped. Here, the field's energy decayed, the spatial expansion rate slowed down, particles and radiation were born, and galaxies gradually formed. However, in the vast regions outside our view, inflation is still ongoing. This is like a pot of boiling water. The whole is still boiling, but continuously generating cooled-down steam bubbles within it. Every time inflation stops in a localized region, a new bubble universe is created. The physical conditions inside these bubbles are suitable for the formation of matter and structure. But in the greater space outside these bubbles, inflation continues rapidly, constantly giving birth to more bubbles. If inflation is indeed eternal, then the entire multiverse would be an infinite collection of bubbles. Image illustrating eternal inflation creating multiple bubble universes. Each bubble universe has its own set of physical constants and structure. Some might have stronger gravity, some might have more dimensions, some might be unable to form stable atoms, and some might be more favorable to life than our own. From a statistical perspective, in a truly infinite multiverse, anything that can possibly happen will happen in some bubble, and it will happen infinitely many times. This makes our familiar concept of probability tricky. When all outcomes are realized somewhere, defining which outcome is more likely becomes difficult. Some physicists argue that the reason we observe the current physical constants is likely due to the anthropic principle. Only universes like our bubble are suitable for the formation of complex structures and observers. In other words, these constants weren't specifically chosen, but rather, only in such a universe would beings like humans exist to ask these questions. This is an explanation tinged with a selection effect. If our bubble universe had collided with another bubble very early on, this violent event might have left traces in the cosmic microwave background radiation. Scientists have tried to analyze the fine texture of the CMB, searching for possible imprints of bubble collisions, but so far, no conclusive evidence has been found. Nonetheless, the idea of eternal inflation naturally bridges the inflation and multiverse approaches in a theoretical sense. It tells us that the so-called beginning of the Big Bang might merely be a local ignition event in a larger cosmic factory, and this factory is continuously producing new universes. When we talk about a vacuum, we usually refer to the state with the lowest possible energy. However, in quantum field theory, a system can exist in a false vacuum, a state that appears stable but is actually only at a local minimum, not the true global minimum. Imagine a hilly landscape with many small valleys and large valleys. A ball placed in a shallow valley will remain stable for a time, despite the undulations around it. But if given a bit of extra energy, or if a quantum tunneling event occurs, it could overcome the ridge and roll into a deeper, more stable valley. The shallow valley corresponds to the false vacuum, and the deeper valley corresponds to the true vacuum. The early universe may have been in such a false vacuum state. Space was filled with a high-energy density false vacuum which seemed stable but had the potential for sudden change, transitioning to the lower energy, more stable true vacuum. This transition can occur through quantum tunneling. In a tiny region, the field suddenly jumps to a lower energy state, forming a true vacuum bubble. Once the true vacuum bubble appears, it expands outward at near the speed of light, consuming the surrounding false vacuum. In the cosmological context, this process can drive extremely rapid spatial expansion. This is one way to explain cosmic inflation. The energy stored in the false vacuum is released during the vacuum decay, causing space to be violently pulled apart like a balloon. If our universe is still in some kind of metastable false vacuum today, then theoretically, in the extremely distant future, a new vacuum transition could still occur. At that time, a true vacuum bubble would form somewhere and spread at an unimaginable speed, rewriting all physical laws in its path. For us, this would mean a complete reset of the cosmic rules, potentially dissolving even the atomic structure. The good news is that, according to current particle physics experiments, if such a false vacuum exists, its lifespan is extremely long, far exceeding the current age of the universe, posing virtually no threat to life. It is more of a theoretical doomsday scenario. Nevertheless, the concept of false vacuum and vacuum decay is crucial because it links the shape of microscopic quantum fields to the large-scale fate of the universe. Whether the universe inflated, how it expands, and whether it will undergo violent phase transitions may all depend on whether the vacuum state is absolutely stable or merely temporarily metastable. In the search for theories of cosmic origin, besides the Big Bang plus inflation, there is an alternative derived from string theory, the ekpyrotic scenario. Image illustrating the ekpyrotic scenario with two parallel brins colliding. The word comes from ancient Greek, meaning, out of fire, or, born from fire. It proposes that our universe may not be the result of a single explosion, but the product of a collision between two high-dimensional brins. In this model, our universe can be viewed as a three-dimensional spatial membrane brin embedded in a higher-dimensional bulk space. Besides our brin, there may exist other parallel brin universes, separated from us by an extra spatial dimension. We cannot directly perceive these extra dimensions, but the brins can influence each other through gravity and other means. In the ekpyrotic scenario, the history of the universe is roughly as follows. Before the Big Bang, two or more brins slowly drifted in the higher dimensional space, parallel to each other and separated by a distance. Over time, some force caused them to gradually approach each other and eventually collide. This collision released immense energy, which was converted into matter and radiation on our brin. For observers on our brin, this instant appears as a cosmic Big Bang. Unlike the inflation model, the ekpyrotic scenario does not rely on a period of extremely rapid spatial expansion to smooth out inhomogeneities. Instead, it suggests that the relative motion and interaction between the brins before the collision had already flattened out the inhomogeneities, leading to a relatively uniform distribution of energy before the collision and naturally generating a smooth enough universe without needing an extra phase of inflation. Further extensions propose that the universe might undergo periodic brin collisions, expansion, and contraction, a cyclic universe. This means the universe does not experience just one origin event, but rather the brins separate in the high-dimensional space, are pulled back together by gravity, and collide again. Each collision ignites a new cosmic cycle. In such a cyclic universe, there is no strict, first round, only an infinite series of cosmic rebirths. In each cycle, galaxies are born and die, black holes form and evaporate, and eventually, everything resets, preparing for the next brin collision and the birth of a new universe. The ekpyrotic model can generate slightly different observational predictions from the inflation model, for example, potentially leaving specific fingerprints in the polarization pattern of the cosmic microwave background's temperature fluctuations. So far, no decisive evidence has been found to prove its superiority over the inflation model, but it provides a completely different route for cosmic origin. The universe was not an explosion from nothing, but was born from the encounter of brins. If our universe is just one of many brins, there could be countless parallel universes in the high-dimensional space, separated from each other by extra dimensions, each with different physical constants and histories. The reason we can only perceive our three-dimensional universe is that all ordinary matter and light are confined to this brin, and only gravity might partially leak into the higher dimensions. The world of our daily experience is composed of three spatial dimensions plus one time dimension. This four-dimensional spacetime constitutes our intuitive reality. But in many advanced theories, these four dimensions are just the tip of the iceberg. At scales we cannot perceive, there may be more spatial dimensions. They played a crucial role at the dawn of the universe. In string theory, the fundamental objects are tiny strings, and their vibrations determine particle properties like mass and charge. However, for strings to vibrate in a way consistent with our observations, space often needs to be 9 spatial dimensions plus one time dimension, or even more. So, where did the extra dimensions go? A standard answer in string theory is that these extra dimensions are compactified, that is, they are curled up and folded into extremely tiny scales, perhaps many orders of magnitude smaller than an atomic nucleus. Image illustrating compactified extra dimensions. It's like a sheet of paper. From a distance, it appears to have only length and width 2 dimensions, but if you roll it up into an extremely thin scroll, from a distance you only see a line, and the third dimension is hidden. The extra dimensions in the universe might exist in a similar way. Although we cannot see these small-scale dimensions, they still influence the vibration modes of the strings, thereby shaping the laws of physics. Why is the electron's mass the number it is now? Why is gravity so weak, while the strong nuclear force is so strong? These factors might be related to the specific geometric shape of the extra dimensions. If extra dimensions exist, our three-dimensional universe might be a brin world within a higher dimensional space. This naturally connects with the previously discussed brin collision, or ekpyrotic scenario. The early evolution of the universe may have been profoundly influenced by these higher dimensional structures. Some energy or fields can propagate freely in the higher dimensional space, while ordinary matter is trapped on the three-dimensional brin. In such a framework, the reason gravity appears to be particularly weak might be that it is not completely confined to our three-dimensional universe but leaks into the extra dimensions. It's like standing in a narrow corridor. If sound can travel to rooms outside the corridor, it will sound weaker to you. Some theories even predict that at sufficiently small distance scales, the behavior of gravity will deviate from the familiar inverse square law because the extra dimensions begin to exert their effect. Although experiments have not yet found significant deviations, related precision measurements are ongoing. In cosmic origin scenarios, the extra dimensions may have undergone a phase transition in shape or size. For example, initially, all dimensions had similar scales, and then only 3 spatial dimensions unfurled to macroscopic scales, while the others remained tiny and compactified. This process of dimensional selection may be closely related to the vacuum structure, quantum fluctuations, and even cosmic inflation, determining why we only observe 3 spatial dimensions macroscopically today. If the structure or topology of the extra dimensions changed in the early universe, they might have triggered changes in the mode of cosmic expansion, or even become the source of a cosmic beginning event. From this perspective, the Big Bang is not just the ignition of three-dimensional space, but the manifestation of a dramatic reorganization of the entire higher dimensional geometry. In traditional particle physics, electrons, quarks, and photons are treated as point particles with no internal structure. This assumption has been successful for a long time, but it faces serious difficulties when trying to unify quantum mechanics and gravity. The point-particle model easily generates infinite divergences in calculations. String theory offers an elegant alternative. All particles are actually the result of the same fundamental object, the tiny string, vibrating in different ways. Like a guitar string, different vibration modes correspond to different musical notes. Different vibration modes of the string correspond to different types of particles. One vibration mode acts like an electron, another like a photon, and a specific vibration mode is interpreted as the graviton, the hypothetical quantum that carries gravity. In this view, various seemingly completely different fundamental particles and forces can be seen as different performances of the same underlying type, providing a natural framework for unifying electromagnetism, the strong and weak nuclear forces, and gravity. Because these strings are incredibly tiny, far beyond the reach of current experimental detection, we can hardly see the strings themselves. But string theory could leave indirect traces on larger scales, such as certain patterns in the cosmic microwave background, the behavior of gravity under extreme conditions, or the peculiar particle spectrum that appears in high-energy collisions, all of which may be related to strings and extra dimensions. From the string theory perspective, spacetime is not a fixed stage but is inseparable from the existence of the strings themselves. The geometric background in which the strings vibrate, in turn, influences the spacetime structure, and the spacetime structure also influences the string's vibration mode. In certain cases, spacetime can even be viewed as the emergent result of the relationships between strings. This concludes our knowledge sharing for today. May you have a wonderful dream and a good day. We will see you next time.